All right, let's dive right into a really wild idea. It's called wave confinement theory, and it asks a question that could change how we see everything. What if mass, the actual substance of our universe, isn't fundamental at all? What if it's just an effect, an illusion created by pure geometry?
And this right here, this is the central mystery. We all know light is made of photons, and photons have zero mass. But an electron definitely has mass. So how do you get something from nothing? How does massless light bundle itself up to create the stuff we call an electron? That's the puzzle we're going to try and solve.
And here is the proposed answer, and it is beautiful. The theory says, what if you take a wave of light and you basically tie it in a knot? You can find it, forcing it to travel in this incredibly tight, looping path. The idea is that once trapped, that light starts to behave exactly as if it has mass. The electron isn't a point particle. It's a self-trapped, knotted wave of light.
So how on earth does that actually work? I mean, how does just trapping a wave create this feeling of substance, of inertia? Okay, think of it this way. Imagine you have a garden hose. Water's going to flow way faster through a straight hose than one that's all coiled up, right? The coils add resistance. Well, it's kind of the same idea here. When you force a light wave into a curved path, its phase gets delayed compared to a wave just zipping along in a straight line. And that geometric delay, that resistance to just going straight, that is what we experience as mass. Now here's the cool part. This isn't just some random effect. The amount of mass you get depends on two very specific geometric properties of that knotted path.
First up, you've got curvature. That's the Greek letter kappa. This one's pretty easy to picture. It's just how sharp the turn is. A gentle, sweeping curve has low curvature. A tight hairpin turn has super high curvature. The more you bend that wave's path, the more mass effect you generate. Simple as that.
But then you've got the second ingredient, and this is what really brings it into 3 dimensions. It's called torsion, or tau. This measures how much the path twists like a corkscrew. It's the difference between a path that's just a flat circle versus one that spirals like a spring. Both the bend and the twist are what cook up the mass.
So what this theory is proposing is a direct recipe. It's saying mass isn't some random number assigned to a particle. Nope, it's a direct function of the geometry of the path that wave is trapped in. It turns it into a calculation, something you can derive from first principles.
And here's that recipe. Now, don't let the symbols freak you out. The core idea is actually incredibly elegant. It says that mass, m, is just the average amount of bend and twist, that's the kappa squared plus tau squared part, scaled by 2 of the most basic numbers in the universe, Planck's constant and the speed of light. That's what keeps this whole thing grounded in real physics. So, bottom line, tighter bends and more twists, averaged over the whole loop, literally mean more mass.
Okay, but here's where it goes from a cool idea to something truly mind-blowing. Mass is just the beginning. It turns out other fundamental properties of particles, things that have always seemed super mysterious in physics, also just fall right out of this geometric picture. Let's talk about spin. You've probably heard that particles like electrons have this bizarre property called spin 1/2. It means you have to turn them around 720 degrees, 2 full rotations, to get them back to looking the same. Why? Well, this theory says it's just a half twist in the wave's path. Think about a Mobius strip. If you trace your finger along it, you have to go around twice to get back to where you started. That bizarre quantum roll, it's just simple physical topology.
And yeah, there's a name for this process. It's called spinnerization. It's not some abstract math thing. It's a literal physical twist in the wave structure. This visual is great. It shows how a simple, untwisted loop could be one type of particle, but you add that single half twist and bam, you've fundamentally changed its nature. You've created what we call a fermion, like an electron.
And it goes even deeper, all the way to the foundations of the standard model. You know those abstract symmetries that physicists use to describe the fundamental forces? They also pop out of the geometry. The U1 symmetry that gives us electromagnetism, that's just the phase of the wave winding around the loop. And the more complicated SU2 symmetry for the weak nuclear force? The theory suggests that's what you get when 3 of these wave loops lock together in a stable resonant triad, kind of like 3 gears meshing perfectly. The fundamental rules of physics become consequences of stable shapes.
Okay, but that raises a huge question, right? Are these shapes just arbitrary? Why these particular knots and twists? Is there some deeper reason they have to be this way?
And it turns out, yes, there is. The theory connects these stable, donut-like shapes to really fundamental mathematical structures. One is called quaternions. You can think of them as a special kind of number perfect for describing rotations in 3D. The other is something called the Hopf vibration, which is like a deep mathematical blueprint for how these loops can exist. The point is, the math shows these knots aren't random at all. They are the most stable, most efficient ways for energy to organize itself when it's confined.
So, let's put all these pieces together. What does this model actually say about a particle we all know and love, the electron?
In this view, the electron is not a tiny dimensionless dot. It's a complex, stable, self-perpetuating wave, what physicists call a soliton. It's a wave that holds its shape. And get this, it's not just one simple wave. It's a coordinated dance of about 10,000 different harmonics of light, all phase-locked and vibrating together in a stable, knotted structure that's defined by its specific curvature and torsion.
And this is how you start to build a universe. The forces between particles are no longer these mysterious fields. They're just the result of their geometric curvature fields overlapping and interacting with each other. It's these geometric pushes and pulls that allow these little particle knots to bind together and form bigger, stable things, like an atom.
Now, you might be thinking, okay, this is a fascinating story, but is it just philosophy? Well, here's the thing. This is a scientific theory, which means it makes real, concrete predictions that you can actually go out and test.
And here is one of the most direct tests. The theory predicts that if you build a tiny optical cavity and you force light to travel along a curved path instead of a perfectly straight one, you should be able to measure a tiny but distinct shift in its frequency. That frequency shift would be the direct signature of this geometric mass effect. It's a make-or-break experiment you can do in a lab.
This slide really just nails the difference. In the standard view, mass is just this built-in property a particle has. In this new view, it emerges from the past geometry. In the standard view, particles are these abstract zero-dimensional points. Here, they're complex, stable knots of light that have actual structure. And maybe the biggest shift, where the standard model has these abstract mathematical rules called symmetries. This theory says those symmetries are just the physical consequences of the geometry. It tries to replace "it just is" with "here's why."
And that leaves us with this one final, truly mind-bending thought. If mass, spin, charge, the forces that hold us together, if all of it is just a consequence of a wave's path, what does that really say about reality? It suggests that at the deepest, most fundamental level, maybe the universe isn't made of stuff at all. Maybe it's just made of pure, dynamic, beautiful geometry.